human exposure to the radio signal. So there's a very specific parameter. It's called specific absorption rate, which every radio devices, including mobile phones, need to satisfy in order to be allowed onto market. Plus we try to discuss that. So after this, so give me a moment. Okay, so yes, today is 21st. So in 1 week, 28, that will be our last meeting with the new content. As I mentioned earlier on the 11th of June, I would like to do a brief overview of all the things that we discussed during the semester and throughout the lecture. Now, of course, this won't be everything that we talked, right? I mean, it will be just like hour and a half, so it will be more to signal the most important things. However, it won't be exhaustive. Okay, so please do not consider that if something will not be on the review, it may still show on the final exam. And then the final exam, the test will be on the 18th of June. So that's our last lecture, same time as lecture. I would propose to have the repetition exam on the 2nd of July. So that gives you basically 2 weeks time for those who well, unfortunately failed to prepare well for the repetition. That's more or less how I would see this to proceed. Are there any questions relating to the content or to the exam?
I have a question. How the exam will look like?
So basically, the exam will be done. Well, it will be unfortunately online exam using our university platform. It will be basically mixture of open questions with the idea of having quite a. I mean, well, okay, I shouldn't say quite a lot, but relatively high number of questions that can be answered using, I don't know, one number or few sentences, that you'll be requested to type into the box, with a little bit addition as well of multiple choice closed question when you'll be expected to tick the box. Right. So, well, typical questions that always show up on the exam is, something that requires the use of link budget. So, for instance, you are given some parameters of antenna, and well, antenna. Let's say the path loss in decibels. Power, and you're requested to calculate, I don't know, some parameter, right, to make the link budget, useful, and all values are predominantly given in decibels. So the math is pretty much simple. But what I'm looking for typically in this test is whether you really do understand the topics. So typically, there won't be any definitions, because I think that's kind of a pointless to just quote the definitions. Rather, it will be focused on, as I said, very simple problems that can be easily calculated within up to 5 minutes time. Okay, so that's more or less the focus of the exam.
And I'm sorry, will you give us a list of topics of what should we cover during preparations, or just everything that was on the lectures?
No, pretty much everything what's on the lecture should be will be on the exam. However, well, as I mentioned, there will be the review, which will focus on the most important aspects, so to speak, right? So even though it won't be exhaustive, and there might be some questions outside of the review, basically the purpose of the review is to put emphasis of what I believe is really the most important, what I would like you to learn from this lecture, right? So I must, well, if you're learning, my advice would be to give like a special attention to the topics covered on the review. Okay, but in the broader understanding, right? So again, understanding of what will be the review without. I wouldn't like that. You simply learn the slides. That's basically my point here. Okay, so learn. I mean, memorize the slides, and if there is some logical conclusion out of that slide that's not on the slide, you stop over there. That's not what I would like. Okay, but in any case, the review will be like the core of what you're supposed to know from this lecture. Does that answer your question?
Yes, thank you.
Okay, thank you. Right. Anything else you'd like to ask or mention?
How long will this test be?
I'm assuming this is something I still need to calculate depending on the number of questions. I would allocate, well, I would set between 1 hour and hour and a half time. So I know actually in previous year there was a little bit issue with the time. Well, issue in the time basically. With the online exams, it was a bit challenging to accurately calculate the time needed for the solution. But I would set 1 hour will be a minimum of 1 hour of writing time. Probably a little bit more. Again, it depends on the final number of questions that will be there.
Okay, thank you.
Thank you. And well, in general, also what I should mention is typically the exam is actually planned as an open book exam, so you won't be allowed to communicate between each other. However, in general, any written materials might be used for the exam. So that's more or less how it is. So I'm really interested in the fact whether you understand the topic, not the definition, and there will be no advanced math. However, I expect you to know decibel scale. So switching between logarithms into linear scale. Of course, we're talking about simple transformation. So basically nothing more complicated than we did a few weeks ago. So 8 watts, how many decibel that is? 10 watts, 3 watts. I will probably use nice numbers that can be relatively easily converted back and forth between linear and decibel, but this is considered actually as something that you should already know before entering this module. Okay, so if you don't feel comfortable, that's also something I encourage you to practice. Yeah. And yeah, so that's it. Okay, so I guess if there are no more questions, then we can carry on.
I have one more question about the final grade. Like, what's the part of the final grade being from the lecture, and what's the part of being from the laboratory classes?
I believe it's dictated.
Just like average, or
No. It's a weighted average. This is dictated actually by this is not chosen by me. Dictated by the topic card. I believe the ratio is actually it's either 60 to 40 or 70 to 30. With of course the 60 or 40% coming from the lecture exams. However, of course, there's the requirement that you need to pass each of this of the parts individually, right? So even if you got like 5 from the lecture and you failed the laboratory or vice versa, the final note will still be, of course, a fail note. That's quite standard. But yeah, otherwise, it's a weighted average. You can look that up in the module card, or I believe it's 70 to 30. But I will double check that maybe before the next lecture to confirm if that's okay. So basically, 70.
Yeah, it's 60 to 40.
Okay, 60 to 40. Yes. Okay, so yeah, that's the same I will use, and that's basically imposed by the department. So yeah, that cannot be changed really. Okay, any more questions? All right. Okay, so I don't hear. So let's move on to the lecture. Okay, so again, can you hear me and can you see the slides?
Yes.
Brilliant. Right. So as an overview again, we talked previously, or we analyzed actually what happens with a modulated signal in frequency domain. So first of all, we were discussing the existence of negative frequencies, and basically the fact that the negative frequencies are real valued, are the consequence, right, of the fact that we are using real valued signal in time domain. Then we talked about Then we talked about modulation. But mathematically speaking, the modulation or amplitude modulation specifically can be seen simply as a multiplication of our baseband or slowly changing signal SM from T by a cosine signal of carrier frequency FC, and that pretty much that multiplication corresponds to moving to up conversion of our signal into the higher frequency, right? So we basically, whatever we have here in the baseband, we are shifting that into the upper frequency with, and because of the negative frequency we mentioned earlier, we will have two peaks, which would be the carrier frequency plus the signal, and carrier frequency minus our signal, obviously with the negative counterpart usual. And then in order to perform demodulation, we repeat the same action, taking actually advantage of the fact that we will have plus and minus combination of the frequency when multiplying, which would result in the signal at the baseband, because the carrier frequency of original signal will be subtracted by the carrier frequency of what we mix for the second time over here. There will be, of course, a high frequency component at double the carrier frequency. So at the end, to extract the requirement baseband signal, we would need a low pass filter just to remove all the harmonics or the undesired intermodulation products, and we stick with our baseband slowly changing signal. So we also looked into the quadrature amplitude modulation. So it was mentioned, of course, earlier on in the slides when we discussed QAM modulation, how it looks from the IQ constellation diagram. And we discussed, how basically it works, right? That you can look also at the QAM modulation using the fact that you have actually two different channels. One is multiplied by cosine, the other with sine function. And because sine and cosine are orthogonal with each other, the two channels can be, again, separated on the receiver side. And that actually allows us to have, pretty much double the amount of information than we would have with single channel. And that's the basis also of the QAM modulation. Then we discussed about a super heterodyne receiver, which is basically another way of demodulating signal that uses the amplitude modulation. With the main characteristic is that it does not directly convert the signal to the baseband, but due to technical reasons, it uses intermediate frequency, which would be somewhere between your incoming radio frequency signal and the baseband signal that you want to recover. So basically, starting from the antenna, you use a filter, a bandpass filter, to tune into the frequency you want to down convert. Then we use low noise amplifier to improve signal strength without adding a lot of noise, hence low noise. And then we apply the mixer with the local oscillator. So that's the first time we perform that down conversion. Of course, the local oscillator and the filter, they can be adjusted because, as even we'll see today, the frequency that we want to receive need to change and tune to different frequency channels. So those two, of course, has to be they're adjustable, but adjustable in simultaneously. Then after the mixer, we apply another bandpass filter. This is, of course, to get rid of the undesired intermodulation products. So double the carrier frequency and basically all of the undesired frequencies generated at the output of the mixer. Here we apply one more amplifier, which can be much more efficient with higher amplification, simply because the frequency used is lower. And then we apply the final demodulator, which in this case, this is a diode that converts our signal back to the baseband. And here again, we use, this is a low pass filter, in order to get rid of the undesired higher frequency components of the demodulator, then amplifier, and then we can use the signal further on. All right. We also talked about nonlinear components. So as you hopefully remember, nonlinear components are actually essential to both modulation or down conversion, or specifically to modulation and demodulation, or up conversion and down conversion of signals. Simply, even from the definition, right? The nonlinear components got ability to create new signals that were not present at the input, which cannot be done with classical linear time invariant systems, such as only capacitors or only inductors. So any frequency change of your signal need requires nonlinear components, and this can be either a diode or more likely transistors, which also allows more stable performance, right? And also sometimes basically better, more efficient, better amplification of your signal. And we also talk about amplifiers and the fact that they have a nonlinear range, which can cause distortion to our signal. So in principle, well, previously we talked about mixer when we actually want to use the nonlinearity of transistors, of amplifiers to perform up and down conversion. However, of course, in the general case, if we are, they can be also undesired effect, right? So for example, if you just apply amplifier to increase your signal, you need to be careful not to put too strong signal at the input, as then again, you might drive your amplifier into nonlinear stage and it starts behaving a little, well, like a mixer pretty much, right? So generating new components at harmonics, at intermodulation products. And then speaking of course, intermodulation products, this is again got to do with the nonlinear range of amplifier, or with it can also appear on a mixer. So basically, if you have two different frequencies at the input of your device, nonlinear device, you might expect intermodulation products at the combination of the two frequencies. So either the different combinations of the two frequencies that are present at your system. However, on this slides, I wanted to highlight the third order intermodulation product. The reason here being that the third order intermodulation product is typically the closest one to your useful signal, right? Because this is double the F2, so double one frequency minus the frequency of the other signal. So basically, as you can see here, the separation between the underside intermodulation product is exactly the same as the distance between the two input frequencies F1, F, and 2. Right. So this can be actually a very significant problem, especially for the new LTE technology or mobile base stations, where for the base station we have to deal with relatively high power. So there is a possibility that the power is high enough to drive amplifiers into the nonlinear range. And since modern mobile communication use quite a lot of different frequencies, again, there is possible a lot of combinations for the intermodulation product. So that is need to be taken into account when engineering the system. Two important figures of merit, which we discussed in the context of amplifier, is 1 decibel compression point and IP3 intercept point, which is so IP3 stands, of course, for intermodulation, third order intermodulation product. And as I mentioned, this is the most often given because of what I mentioned earlier, that this is actually the most dangerous, the most difficult to filter because of the proximity to the useful frequency. So are there any questions so far? All right. So since there are no questions, we move on now to the basics of the mobile communication and the cellular system. So we are discussing some main principles, and basically this idea that if you want to cover huge area with a radio access network with the communicating to mobile users. It is actually much more efficient to do it by dividing the area into small areas or small cells, as it's called in this context. And overlapping cells will cover all of the area and operate as a system. And that gives you a certain advantage. So even though the initial deployment cost and construction of multiple transmitters might be higher, at the end of the day, you have to use less power simply because of the coverage of lower area. Again, going back to the fact that the distance, the power is attenuated with the factor of power 2 for the lossy case. And also each of those transmitters can pretty much use or recycle different frequency to serve different users. Okay, so and today I wanted to discuss a little bit more the concept of what's called frequency reuse. So this is exactly the thing that we had here, that it allows to increase the traffic. You can serve much more users or much more devices than with a single transmitter, simply because you can use same set of frequencies between multiple cells. However, the challenge is you don't want to create interference or too much, of course, interference between the cells. That's always the risks. So there is a need for a careful planning of your radio signals. So before we discuss how such a cell systems can be planned, just maybe a few definitions or a few terms that will be used here. I mean, some of them are probably known to you. So when we basically talk about mobile station, this is the user transceiver terminal. So by transceiver, we mean a device which is both transmitter and receiver, such as your mobile phone, handset. This is defined as the mobile station simply because it is more general than just your phone. So the connection may be, for example, between elevators. That's quite common for the emergency calls. So when you see the red button in the elevator that you can press when you get stuck, this typically uses a mobile network to make the call. Many assets, especially cars, expensive cars, they would also contain a GPS system for tracking purposes. Also, I know many lorry companies, they also equip their cars in the GPS system to track the location of vehicles. It can be also in the form of if somebody steals a car, right? It might be a part of anti-theft system. However, basically the GPS receiver, the GPS systems, it is only a receiver, right? So it allows you to get the location of the asset. However, you need to be able to transmit that location to the controlling station, and that's again typically used through cellular or mobile network. Hence, that we also consider the mobile station. Okay, the base station. This is basically the station that receives the call or any form of communication. Really, it's a fixed transmitter which carries makes the wireless connection, and then passes it on to the access network, and then to the core network. they're actually quite easily recognizable as, with the white panel antennas, which are, it's actually a vertical antenna arrays that you can see on top of buildings. That's the base station. Now, mobile switching center, this is simply, the center that carries the call and basically makes the connections either to the classical PSTN, it stands for Public Service Telephone Network. So basically, we're talking here about landlines telephone. It can be carried into the internet, especially if it's a data connection, or it can be also carried into a different base station. If you, which is the case if you're calling from one mobile to another mobile. Typically, the phone would be carried through a base station to the mobile switching center, then it would be directed to another base station. Okay, that's the. Now, control channels. This is basically the channels which are used internally for managing the whole system. Okay, so when you pick up the call, you might want to monitor neighboring base stations, for example. You might like to monitor certain aspects of the system. We'll talk about that in a few slides. That's carried on through control channels. Now, important definitions again. So downlink and uplink, or forward channel and reverse channel. Okay, so typical communication in a mobile system, it's carried two ways. So both base station and UFO can transmit and receive. However, the characteristic of the traffic is much different in the sense that with the base station. So if the base station transmit, it typically uses relatively high power, directional antenna that can be with high gain that can focus the energy. On the other hand, your mobile phone, this is a small device with antennas that are not very efficient, and very often when you can cover the antenna with your hand, which would add some attenuation to the phone. So the gain of a typical mobile antenna will be actually really very low, even below 0 decibels because of the losses that occur. So with that regard, we distinguish between downlink and uplink. So downlink is the transmission of information from base station to mobile station, whereas uplink is the reverse. This is the communication from your phone to the base station. It actually the term comes from the satellite communication, but it can be still applied, to the base station network. So a simple mnemotechnique to remember which one is which is to keep in mind that still most of the base stations are located on the top of the buildings, right? So basically, if the base station communicates to your mobile phone, that would be lower. So that's downlink because the link is going down. The uplink, the link is going upwards from your phone to the base station that typically is located higher than your phone. So that's a simple way to remember which one is which. Okay. Right. And then handover. Okay, so this is something that that popped up in some of the previous lectures. Typically, we know that using multiple cells is advantageous. It offers you can serve multiple users. You can reuse some of the frequency, some of the resources. However, the negative side effect is, of course, that if you move from one cell to another, you typically don't want your customer to disconnect the call and call again once they reach the new cell, right? You typically want to make the technical aspects unnoticeable for the customer, so that they can see the same of quality of service, regardless of whether they're in the middle of the cell or at the edge of the cell. And this is basically what handover is doing. So handover is a set of protocols designed simply to seemingly move the connection from one base station to another, so that the customer doesn't even notice that that the switch was made. Again, we will talk about that in more details in few sections. Then paging, this is a term for a generic message broadcast over entire area. So this includes, for example, as an example is an emergency channel. So if you get emergency information that there is a storm coming, or well, at the last elections that some people do not need to queue when polling. This is an example of paging. However, here this is of course broader term. So pretty much any messages that is not user to user or point to point, but broadcaster to the broader area can be considered paging. And then roaming. This is, well, commonly referred to when you're like using your phone abroad. But again, this is just an example. So formal term is basically when your mobile station or your phone operates in a service area that you're not subscribed. And the reason why this is significant is that on the technological level, there is a certain slightly different set of procedures. So, and again, this is mainly in the context of going abroad. When you move abroad and your mobile phone provider has the agreement with your Polish or home country provider to carry the calls. This may also happen sometimes when you are even within the country. So, for example, if there is a network which uses secondary network for coverage reasons, right? So, for example, you got that's especially the case with cheap mobile providers. If they want increase the coverage, they might actually, rather than deploying their own base station, they might like to sign a contract with the bigger provider to redirect the calls through them. And the reason why it is highlighted here or mentioned here is that there is a slightly different technological challenges here, because in that context, when the call is made, the phone connects with the external roaming provider, okay, so normally the call would not be recognized. And what happens if, of course, there is a certain agreement in place, so let's use the international example. So let's say you're making a call from Germany while having Polish mobile subscriber. So what's happening is that typically your data and information about your phone would stay in the center in Poland. And basically you're connecting to the German access network, which simply would pass your data to the routing or to the mobile center that is in Poland of their partners. So they are basically transferring your information, and the call basically is not routed through their core network. No, sorry, the call is not managed basically by them. That's what I wanted to say. Okay, so that's it for the definition. again, any questions relating to the basics or the definition that we will use from now on? Okay. Yeah, I mean, I guess most of them were, at some intuitive level already familiar to you, and many of those terms, are present in the common language. So it's just of quantifying. Okay. So anyway, the frequency reuse. So let's assume we have coverage of a certain area with multiple cells or multiple base stations, and we want to plan our frequencies and assign the frequencies to each base station in a way, to maximize the number of customers that we can serve. However, also we want to avoid interference. Okay, so well, the first, of course, intuitive approach is that when we have neighboring base stations, it is preferable that they do not use the very same frequencies, because as I mentioned, the radio signal deteriorates with the power too of the distance. So of course, obviously the closest stations will be the ones that are the most impacted. So what we can also do, we can play a little bit with our antennas in the sense that if we make the antennas more directive, they will cover a smaller area. However, with proper design, this smaller area can be again used for the frequency reuse. Right. So if there is a sufficient separation, again we can multiply our resources if there is a large enough distance between them. Okay, so anyway, let's move how the radio planning is typically done. So first of all, very often we do the planning using a hexagon. So obviously, again, this is some theoretical limit. However, hexagons are a very convenient tool. Of course, the real cells are never hexagon, and the size of the cell will also depend on the propagation aspect. So especially in urban canyons, in mountain area, you will have a very strange shape of the cells, simply because of the obstacles to the propagation, as we discussed in the radio channel. Okay. So, however, well, they're convenient because there are polygons, right? So they can nicely fit together, and still they are polygons which resemble circle the most, right? So typically, actually, if you take the radius of the circle, you can actually enclose a regular hexagon where the side of your hexagon is the same as the radius of the circumscribing circle of that hexagon. So that's pretty much a convenient tool. And also they can, as I said, represent the contour of equal transmitted power. Again, for the moment, we are assuming that we are operating with free space and ignoring the propagation aspects that of reflected signals from building, mountains, etc. Sorry. Then what we do, well, we have our area split into the hexagons, and then we create clusters. So the idea is that cluster consists of n different cells, which use the frequency recyclings, in the sense that within one cluster of cells, there is no two cells with with the same set of frequencies. And the number of n denotes the number of cells in a single cluster. That is, but also it defines as the set of frequencies that we can use here. Okay, so typical number for the cluster size n is it's actually given by this equation. So I to the power 2 plus minus ij plus minus j to the power 2, where I and j are different integers. So at the end, we can have clusters that have 3, 4, 7, and 12, and so on, number of cells within a cluster. And as we'll see later on, this is dictated by the topology. So by the fact that the main rule is you want to avoid having same frequencies next to each other. Okay. What's also important here that the cells can be normal or sectored. In the case of a sectored cells, it means we have multiple antennas, each antenna looking kind of independently into different sectors. Okay. So within a cluster, each cell has a set of different frequencies. So no frequency can be repeated within a cluster. And typically more cells in a clusters mean less interference, okay? Simply because the same frequencies are reused over longer distances. So once the power already decays, typical sizes of clusters are 7, 4, or 1 for ones for the CDMA system. Of course, this is a little bit specific case, but it as you can imagine, and it came later on with the evolution of systems. However, yeah, we have so 7 and 4 clusters are, if you think about it, this is relatively low numbers, as in here, and from the point of view of avoiding interference, one would actually expect that the larger number of clusters mitigates the interference, right? So why actually such a low number? So why not keep increasing the numbers of cells to why not using clusters with 12 cells or even higher? Why do you think is that? Any ideas? Okay, so if you basically imagine that one cluster allows for frequency reuse within certain area, and what you're doing is that if the distance between two cells using same frequency is increased, this means lower frequency reuse over the same area, and that lower frequency reuse is the thing that limits our interference. Okay, but the same principle, how do you think it will affect number of users? what would happen with the numbers of the users you can serve when basically the number of cells within a cluster increases. Okay, so let's make a question here. Okay, so so which of those three answers you think is correct? As usual, you can vote through like button or any other icon you choose. Sorry, of course, one more. Of course, the first and two are pretty much the same. Okay, well, only one answer. Anybody?
Isn't it like, I mean, if we were increasing the power of the single base station, at some point it was useless because the power was increasing, and then the interference, this signal to noise ratio, yes, am I right, was increasing, and it was pointless. So we were doing like multiple base station, but of lower power. And in this time, if we will like increasing these clusters, then I think at some point it will be so big number of cells that the frequency, I mean, we won't be able to reuse the frequencies at some distance, and the distance will grow. So one cluster will have to serve the more people and more cells. So I think it will be like overloaded, maybe.
It's okay. So I think you raised quite a few issues here. So firstly, yes, you can increase the power of your transmitter. However, well, typically there are some legal limits of on doing that, right? And the idea is, of course, that if you increase your transmitter, assuming the same frequency, you're generating also more interference at those frequencies. I feel I'm not quite sure, but I think you pointed out actually to quite accurate thing in the sense that if you enlarge your cluster, you would so let's assume, for instance, you have 12 different frequencies, right, that you bought from the government and that you're legally entitled to use. And I think that's what you meant, right? That when the size of the cluster increases, you reuse those 12 frequencies among higher number of cells. So with this set of 12 frequency, without repeating, you're covering a larger area. However, the problem is that you have to divide those frequencies among your clusters. So at the end of the day, each cluster, each number of cells, right? And that means each cell will use smaller number of frequencies. I'm sure, is that more or less what you meant here? Or
I think yes, but because I understood that each cell in the cluster has its own frequency. So if we have like 12 cells in the cluster, we have 12 independent frequencies.
Yes, that's correct, right? However,
I understood also that we can't, if there are like those hexagons, and we'll put two certain frequencies which are the same next to each other, it will make the interferences. So we can't use this certain frequency next to each other and next to some distance, which will grow with the increasing cells. So and also if we are the owners of some frequency, we have limited laws to these frequencies from the government. So we have to like manage with this number, and I think we have to optimize this number of cells in the cluster according to our like resources.
Yes, exactly. That was pretty much exactly what I was trying to tell you, right? So the story is in a nutshell, right? That you or the consequences, assuming this 12, assuming we bought, let's say, 12 frequency channels, just using this example, we can have clusters of 12 cells, which each cell will use one frequency channel. However, if we, and then the interference would be, of course, very low, right? However, if we kind of squeeze the cluster and use cluster with only 4 cells, then each of that cells can use 3 different frequencies, right? Out of those 12 that we bought from the government, okay? And if a single cell can use 3 different frequencies, then we can practically serve 3 times as much users as we use with single frequency channels, right? That's the philosophy here, right? Is that understood?
Can we also say that the more cells in the cluster, then less peak bandwidth can be given to one user, even if the usage of the network is low?
Sorry, can you repeat your questions? Sorry, no, I just haven't heard your question. Can you repeat it, please?
So the more cells in the cluster, the less peak bandwidth can be given to one user, even if the usage of the network is low.
Yes, pretty much yes. Or we can serve if we yes. Yes. If you think about adaptive systems, when you can change the bandwidth given to one user, that's what would happen, right? Or equivalently, if the bandwidth to each user is fixed, right? That means you can serve less users because you use the same bandwidth. Well, you use same bandwidth for users. That's correct. Okay. And okay, and so yeah, and basically this is the reasons why the cluster size are typically relatively low, right? Because well, at the end of the day, every provider gets money by serving more users. So The issue of interference is kind of secondary. I mean, well, of course, if it kicks in badly, then you cannot serve any users. But in general, this is exactly the reasons why typical clusters, especially in urban areas in big cities, are relatively small, is that it allows more frequency reuse, allows you at the end of the day to serve more users within within same set of frequencies. And so at the end of the day, it's a kind of a trade-off between interference and number of users. And I hope with these slides everything should be more clear. So here we have the division of one cell. This is pretty much hardly any frequency reuse, but it actually maximizes the throughput. So we can serve, we can allocate all the frequencies over here. So that's cluster N1. It's pretty much any reuse. So in the case of 4 clusters, we have A, B, C, D. So that A, B, C, D corresponds to the different sets of frequencies that we're using. And you can see here that, let's say, a distance between 2 A's is just 1 cell. If we increase that, here, of course, we have the 7 different cells, A, B, C, D, E, F, G.
I'm sorry.
Yep.
I don't. Do you share a presentation?
Yeah. Okay. Let's give me a second. I will just restart. Maybe if that's. I believe I was sharing, but I might have been wrong. So once again. Okay.
Now it's okay.
Brilliant. Okay. Yes. So this is the comparison I was talking about, right? So in the case of 4 cells over here, where you can see the distance between 2 A's is 1 cell. If you increase that to 7, here the distance between 2 A's, it's let's say slightly less than 2 cells if you count it in the straight line, right? However, as I mentioned, if you keep in mind that in all those 3 cases you use the same number of frequencies, well, here you divide all your frequencies that you bought by 4. Here you have to divide them by 7. So at the end of the day, each cell uses smaller number of different frequencies, which translate to the lower communication throughput, right? Because hopefully from the Nyquist and the channel theorem, more bandwidth you got, more communication you can transmit. And then, of course, whether you allocate all to one user that needs more resources or you divide that to multiple users, that's kind of a secondary, the consequence of that. All right, so in general, that's how it look. Of course, area coverage. So you typically, you typically try to have a regular repetitive grid which supports the planning of the network. And that, as I mentioned, like those topologies are designed in a way that no 2 sets of frequencies can be next to each other, and that's apparently possible only with the numbers that basically satisfy this requirement, those criteria. So with 3, 4, 7, 2, but basically you cannot do this with, let's say, 4 or 5 with cluster size of 2 or 5. I think for 2 it's obvious why and intuitive why you cannot do the cluster without having two cells next to each other. However, for 5 and 6, it's also not possible. So it is not using the hexagonal shapes. All right. Okay, so I guess so far is clear. Now I wanted to move on to the issue of handover. So, well, basically how to do a handover. And for that, there is a broadcast control channels, or abbreviated as BCCH, which is basically, there's a one frequency channel which is allocated into basically technical issues. Broadcasting basically means that it is not private, so not user-to-user connection, but rather, this information will be transmitted indiscriminately to all servers or all mobile stations that are within area. Secondly, within our system, this BCCH, so broadcast control channel, will also use different frequency between different cells. So it pretty much follows the same frequency planning how it is used. Okay, so basically how it works. Well, we have here a mobile station which is connected to the base station number 4, and is within the cell. And typically it knows the cell, and this cell here is communicating useful information using channel number 7. That's just arbitrarily frequency allocation. Okay, and the phone would receive and demodulate information from this channel number 7. And well, what is broadcasted through that channel? Well, many things. However, one of the broadcasted information would be the channel list or numbers of BCCH of neighboring cells. Okay, so by demodulating and receiving the information from the channel of the main base station number 4, the phone knows that neighboring cells communicate BCCH using channel 1, 2, 3, 4, 5, and 6, which is here 1, 2, 3, 4, 5, and 6. All right. Well, so far so good. Now, what the mobile does with this information? Well, typically it got limited number of demodulator or receivers. So it is tuned to demodulate into only one channel, 7. This is called the monitored channel, meaning it actively demodulates the information. So the mixers and the bandpass filter are tuned to that particular frequency. However, without demodulating, it can also simply monitor the power on all the different frequency channels that were, that it was informed that are the frequency channels of the broadcast control channels of neighboring base station. Now, for stationary case, this is quite obvious. Let's see what happens when our users start to move eastwards. Okay, so as the phone reaches edge of the cell, of course, the power received from the main cell will drop. So you can see here. And of course, the power of the signal that is of the neighboring cell will increase.
I'm sorry.
Yes.
I think it's something wrong with your sharing, because it's stuck. It was stuck on the same, like the picture, and when I leave the meeting and then came back, it's just like you're sharing back. It's black screen. So, and then My colleagues say they see the same thing.
And I lost the presentation completely. I can see it, and also left and came into the meeting.
Okay.
We try starting Teams.
Yeah, I will. Okay, so give me a second, and I will. Mhm. I just double check the. Is it same now or?
It's working for now.
All right. So well, let's keep it. I mean, well, we get 15 minutes left. But okay. So can you see moving? Well, moving mobile phone basically. That's the only thing
Yes.
that changes.
Yes.
All right, brilliant. So let's try to carry on. Anyway, thank you for. So yeah, if you notice the same problem, just speak. Okay. So yeah. Anyway, our base station for like the phone move or the user moves to the edge of the cell. So understandably, the power of the main cell deteriorates, but it is still the most dominant, the strongest component. Right. The other. The power strength of the BCCH signal from neighboring cells. So channel number 4, which corresponds to base station 7, increased because we are closer to the base station, but it is still not the dominant. So now what happens to switch? So basically we moved on to the base station number 7, which we can see that the power of signal number 4 became stronger than the channel number 7. Okay, and this is exactly the moment when our phone says bye-bye. So what it does, it says, okay, look, I got better signal now from the stronger signal from base station number 7, which is on the frequency channel 4. So I will make a switch to that base station. Can you please arrange that with the network, right? And then basically the network would create a new connection through base station number 7. The original connection will be, seemingly transferred to the new set of frequencies, and the receiver in the phone would detune to monitor now channel number 4. Okay, so basically now we switch the active monitored channel, which requires change of the mixer filters in the phone and so on. That's done reasonably quick. It now demodulates channel number 4, and all the other channels with the channel number 7. Actually, it demodulates channel number 4. It gets updated list of neighboring frequency lists because those 3 base stations are irrelevant right now. However, we get base station number 8, 10, and well, once again 8. Anyway, those 2 base stations that will be included now in the list of the control channels that are monitored through only by power. Okay, and this is basically how the transfer typically works. Okay, now bear in mind that of course there is typically some sort of mechanism to prevent temporary jumps between the cells. So when we're at the border, there's a certain protocol that of course the signal needs to be stronger over a certain amount of time. Otherwise, when you're exactly at the border, it would be flipping between the 2 base stations, which is not very useful. But Other advantage is that it allows, simply monitoring of the radio frequencies. So at the end of the day, the mobile phone does not need to know neither which direction it is moving. I mean, physically, it doesn't need to know about the shape of the cell, because it simply uses measurement of direct radio signals. So if we would change those shapes to any other shape, it could be, well, pretty much whatever. It doesn't need to be a hexagon. The same principle would still be used, right? Because then, of course, the size of the cell is basically defined by the power of the signal that can be received, right? So it's done seemingly, and that's a very, very efficient tool. So any questions relating to the handover? Okay, I can see. So a few more things. We got 10 more minutes, but well, I hope we should finish off with the mobile station. So important thing is that with the mobile new generation of mobile communication, I mentioned already that the cells do not have to be exactly hexagons in practical terms. However, in general, they do not need to be also the same size. Okay, and this is something which we can have, multiple layers of cell and multiple sizes of cells. So typically in huge cities, when we're serving multiple users, we will have smaller cells, of course, transmitting even less power. This got to do firstly with the requirement to serve even more users, but also the propagation environment is much more challenging. So if the channel is complicated with multiple reflections, it is simply easier to have the smaller cells and split the area even further. Whereas, if you move to suburban areas outside of the city, well, then you have less users, but also your propagation channel will have smaller delays due to less reflections. So the cell can be also larger. This is somehow linked to the different types of propagation channel that we discussed few slides earlier on. So in general, we can talk about femtocells, microcells, depending again on the size. So, another thing is that I already mentioned to you that GSM, this is one of the first standard that was used, and I mentioned a few times when we discussed multiple access techniques that GSM use TDMA or time division multiple access techniques. Well, this is true, but it's not all of the true. So as a matter of fact, with a growing number of users, the GSM would use a combination of FDMA and TDMA. So in terms of the frequency division duplex, so that means that the uplink and downlink frequencies are separated typically by 45 megahertz. For the GSM 900, this is 900 megahertz bands of the GSM, or 95 megahertz for the 1.8 gigahertz GSM standard. And typically, and each frequency channel would allocate basically 200 kilohertz. Okay. Now, within each of those frequency channel, there would be a time division multiple use. So as can be seen here, the frequency is divided into 8 different frames, which keep being repeated. Each different slots, 8 different slots within a frame. Each frame takes 4.6 millisecond, and each time slot is 577 microseconds. So those times, of course, were designed in order, to carry the data without interrupting speech, right? So, as a matter of fact, when you speak over your phone using classical, I'm not talking about like WhatsApp, but when we talk about the classical phone, actually your phone would not transmit continuously. It will transmit at a certain frequency, only this amount of time, so slightly more than 500 microseconds over the duration of 4.6 microseconds. So actually it's a very, if you look at the spectrum of the transmitted power, this GSM, time division multiplexing, would be seen quite characteristic as simply a signal burst in regular intervals. Then for technical reasons, there will be also shift between uplink and downlink by 7 time slots. Well, that's sorry, that's some sort of technical detail. But in general, what I would like you to remember from this is that GSM is a combination of FDMA and TDMA, using multiple frequencies, as we actually discussed earlier on today. And each frequency channel consists of a frame, each frame consisting 8 time slots, where each slot here is assigned to different users, right? So as you can see, really the GSM was built in order to maximize the throughput or the ability to serve as many users as possible. Any questions so far here? Okay. And then, well, here basically the details of the TDMA. So again, those are technical parameters. As at the time were assigned in a way to that there's no noticeable delay when you speak, so we can have comfortable conversation, while also taking into the account the effects of the channel and multiple reflections, right? So in of the channel, and as we said, most of the time the terminal is inactive. It just like transmits burst within one slot every frame, which consists of the 8 slots. There are some challenges related to that because of this very short transmission time. Both your mobile phone requires very rapid switching on off and off, because if the transmission takes too long, you might actually interrupt within communication of other users. There are, of course, some guard time to prevent that from happening, but still, they are limited in capacity. Secondly, there is a synchronization required to make sure that every phone is synchronized and know their time slot. So, for example, this basically comes from the fact that the radio signal, it travels at the speed of light, right? However, of course, there will be a delay simply if 2 different terminals are located at different distances from the cell, right? So there is a certain synchronization mechanism required here. And also another challenge is that there is a possibility for the wide byte interference. Okay, and this is something that comes from the fact that, well, it basically is a consequence of the first point here. Because of the relatively short time slots, we need to switch our signal on and off very quickly. which means very short time response of the filters of all the electronics. And as we talked earlier, short time response, how they will be seen in the frequency domain. Well, basically quick switching time means wider frequency spectrum. Okay, it's again the very basic principle we talk over and over throughout this lecture, that if you want things quick, your frequency, your bandwidth need to be larger. So that's also something that need to be taken into account here. Okay, and I think I can skip through that. So those are just example of frequencies assigned to different mobile providers. And I think we don't really have time for those, so I'm afraid we will have to skip through those slides for today. Do you have any questions so far? Okay, well, I guess there are no questions. So, well, with that, if you may do once again, thank you for your participation in the lecture. And the consultation time will start as usual at 1 p.m. Well, I'm expecting, since we are nearing to the examination, that they will be more commonly used. Again, at any stage, you can write me an email with with the questions that you have, and I will try to answer as quickly as I can, or as my as time allows. Okay, so okay, so well, with that, since there are no more questions, thank you very much for attending, and have a nice weekend. Thank you very much.
Goodbye.
Goodbye.